So thermodynamics is the study of energy. It's the prefix therm. And it's interconversion, dynamics, things changing. So the first law of thermodynamics is the law of conservation of energy. Another way of stating that is the total amount of energy in the universe is constant. So you can never come up with a system that will produce more energy than it uses. It's not possible. You cannot get something for nothing. We sometimes refer to this as there is no free lunch. You might say, yeah, but in my elementary school, we all got free lunch. Was that lunch free? No, someone has to pay for the lunch, right? Who pays for the lunch? Ultimately, the taxpayers are paying for your lunch. It's not free. And the second law of thermodynamics, which we cover in Chem 1B, is even more depressing. You can't get ahead. There's no free lunch, meaning you can't get ahead, and you can't even break even. So you can't get ahead and you can't break even.
So does that mean that fusion research is just trying to break the laws of thermodynamics?
Actually, no. So this applies to chemical processes.
Okay.
Yeah. Nuclear processes, completely different. So in a nuclear process, you can convert matter into energy. Yeah. And that's where Einstein's equation E equals mc squared. Energy equals the mass times the speed of light squared. So a tiny bit of mass, huge amount of energy. So you have to put, when you're talking about all possibilities, you have to put conservation of mass and energy together and say that the total of mass and energy in the universe is constant. But those can also interconvert. But we set that aside because we just do nuclear chemistry in one chapter. It's very interesting, but so we have to talk about state functions. A state function is something that only depends on the difference between the initial and the final value. It doesn't matter how you got there. So elevation, change in elevation is an example of a state function. So here we have a picture of a mountain, and we have people hiking up path A, and they are going to travel a distance of 12 miles as they get to the top of the mountain. And then we also have a couple of crazy people going up path B, which is going straight up the side of the mountain. They're only going to travel 5 miles, but it's going to be harder, right? They're starting at 0. They're going to end up around 10,000 feet. It doesn't matter which path you take. When you get to the end, the change in elevation is the same. The distance traveled is not the same. Distance traveled is not a state function. That depends on how you got there. Which way did you go? But the change in elevation only depends on the starting point and the ending point. You could also hire someone to come get you in a helicopter, and you go up and over and down. And the distance you travel is different than the other people, but the change in elevation is the same. I'm giving you lots of little pieces right now, and then we're going to pull them all together. So internal energy, symbolized with E, is the sum of the kinetic and potential energies of all the particles that compose the system. The internal energy of a system is not something that we can measure easily. It's very difficult. But internal energy is a state function. So the value only depends on the state of the system and not how it got there. So we can look at the change in internal energy, and like the change in elevation, it's just the difference between where it is now and where it was before. And it doesn't matter what happened, how it got there. So we say that delta E is E final minus E initial. And this triangle is a capital Greek delta, and it means change in. And it's always the final minus the initial. So with the change in elevation, the final elevation is 1,000 feet. The initial is 0. So 1,000 minus 0, you have a positive change in elevation. If you were at sea level and you went down, your final would be maybe minus 1,000 feet, and the initial is 0, you subtract 0, and the difference is negative. That means you went down. And so the final minus initial is important. So in a chemical system, we can think about the reactants as being the initial state and the products being the final state. So here we have the combustion of carbon reacting with oxygen to form carbon dioxide. The internal energy of the reactants is at this level. So this is called an energy diagram. It's not really a graph because there really aren't any numbers or anything. It's just sort of showing big ideas. And so we represent internal energy going up as you go up on the screen. So here we have the carbon and the oxygen. The reactants are up here, and the product is down here. It's lower in energy. So in the process of this reaction, it went from here down to here. The final minus the initial is going to be a negative number. And what that tells us is that energy left the system and went into the surroundings. It's like a negative change in your bank balance. So if we look at the change in energy for the system, it's negative. The change in energy for the surrounding is positive. The change in energy for the reaction is the energy of the products minus the energy of the reactants. So the system and the surroundings are like, if I was going to give Mary some money, I'm going to give her $5. For me, that's a negative because my net worth went from whatever down $5. And for her, that's a positive change because hers went up. Does that make sense? That's what energy goes from one thing to another. One goes up, the other goes down. We can also look at the opposite process. Wait a minute. No, that's the same process. Sorry. I'm thinking ahead to that one. Lost in my slides. So the energy lost is gained. The energy lost by the system is gained by the surroundings. So the system lost energy, so its delta E is negative. The surroundings gained energy, their delta E is positive. So we can relate those two this way. Delta E surroundings is equal to the negative of delta E system. This is not saying that delta E system is a negative number and that this is positive or vice versa. It could be any combination. It's saying that they are equal but opposite in sign. Does that make sense? Because if I give Mary $5, that's minus 5 for me. So let's say that I am the system. So the change in energy for the system is minus $5. That's a pretty sad looking 5. So if Mary, do you mind me picking on you? No? Okay. You have a nice neutral name. If Mary is the surroundings, what's delta E for her? it's minus 1 times negative 5. So it's positive 5. Okay? This is a very, very simple mathematical equation that I find is misunderstood by most students. I think maybe because you overcomplicate it or something. These two things are equal, but they're opposite in sign. Okay, that's all it's saying. So if we reverse the reaction, now instead of the carbon and oxygen reacting to form CO2, the CO2 is reacting to form carbon and oxygen. It's the opposite process. So the CO2, the reactant, is lower in energy, and the products are higher in energy. Because carbon and oxygen, regardless of what you're going to do with them in a reaction, they have an internal energy. They have a chemical energy that is dependent on the relative positions of the electrons and the nuclei within their atoms. And that part is independent of its temperature or its position or anything. And so we can always look at the relative position of these three substances. So CO2 is lower in energy, and carbon and oxygen are higher in energy. So in this process, we're going from down here up to here. The final is higher minus the initial, and here delta E is greater than 0, it's positive. So then the system is gaining energy. That energy has to come from somewhere. It comes from the surroundings. So the surroundings is the same number, opposite in sign. So this time the surroundings is negative and the system is positive. It's the money going the other way. That's positive for me and negative for her. That's an excellent question. How do we know what the energy of this is, and how do we know it's less than these? We'll get into that. Yeah. Any other questions? So summarizing energy flow, if the reactants are higher in energy than the products, then the system loses energy, and the change in energy is negative. It goes out of the system into the surroundings, and then the opposite for lower internal energy to higher. So it's like money. The system is like your bank account or your wallet. Money coming in is positive, right? I love it when money comes into my pocket or my wallet or my bank account. When money goes out, it's kind of negative, right? And regardless of your feelings about it, if you look at your bank balance online, because we don't have check registers anymore, right? You look at your bank balance online and you see positive this and negative that. And that tells you which direction the money went, right? We're doing exactly the same thing with the energy, okay? So consider these fictitious internal energy gauges that describe the initial conditions for a chemical system and its surroundings. So here's our chemical system, and here's the surroundings. So the chemical system has 3/4 of a tank, and the surroundings has 1/4. So which of these, A, B, C, correspond to the final condition following an energy change in which delta E's system is negative? So the change in energy for the system is negative, meaning the system is losing energy, right? So the system was 3/4 full. After this transfer, it's going to be less than that, right? And we have no information to say how much less. But the change in energy for the system being negative, and we look at this one over here and we say, well, that one's wrong. Because here, the energy for the system got larger. So that one's wrong. We can get rid of that option. A and B, we see the energy for the system has gotten smaller. It's less. Well, when the system gets lower, what happens to the surroundings? It gets higher, right? So in example B, the chemical system got lower in energy and the surroundings stayed the same. That's not possible. Because if $5 comes out of my wallet, it has to go somewhere. And even if another person doesn't get it, it's like sitting on the sidewalk that's in the surroundings, right? The rest of the universe has my $5. It doesn't just disappear. So this one, whoops. Yeah, that one can't be correct either. This one must be the right one. Where the system went down and the surroundings went up. Does that make sense? So heat and work. Heat and work are ways that energy is exchanged. They are not state functions. The change in energy is, or the energy is a state function, but the heat and work are not state functions. So we can look at it this way. Here we have our system and our surroundings, and heat can transfer energy in either direction, and work can transfer energy in either direction. And so we've got this little relationship. The change in energy is equal to the heat plus the work. So we have to define signs for these, positive and negative. So sign conventions. We already talked about delta E. Delta E is positive when energy flows into the system, like it's a positive when money comes into my bank account. Energy flows out of the system, it's negative. Q is positive when the system gains thermal energy. So it's getting warmer. It's gaining thermal energy. So if we think about the hand warmer and my hand, if my hand is the system, it's getting energy, so it's positive. Q is positive. If we look at the hand warmer, it's releasing thermal energy. It's negative. Q is negative for the hand warmer. And then work. So here we can think about this as being similar to work, where I go to work and they pay me money. Or someone does work for me. Like if I have a housekeeper come in and clean my house, is that a positive for me or a negative? That's a positive. It's like my house got clean and I didn't have to expend any energy, right? Or I can go to work and clean the toilets in the science building, right? Ew. That would be a negative. I'm putting out, it's negative. So that's a sign on work. Work being done on you or for you is positive. Work that you are doing is negative. So we're just going to feel a little bit lazy when we think about that. So let's look at those billiard balls again. So here we have a pool table, and we have this white ball, and it has some initial kinetic energy. Probably got hit with the pool cue, and so it's moving across the table. As it moves across the table, because this is a real table, there's some friction here, and some of the energy from this ball is lost as it rolls across the table. Because if you roll a ball, will it roll forever until something gets in its way? No, it will slow down on its own because of friction. So it's going to lose some energy as heat in friction. And if you're not familiar with that, just rub your hands together really fast. Nobody's doing it. Oh, good. It's cold in here. You feel it warm? It's warm. Where's that heat coming from? The kinetic energy of your hands moving is being transferred into heat that goes into your hands, right? It's like, oh, nice and warm. So as the ball is rolling, there's friction also. We probably just won't be able to tell that it's getting warmer. The table's getting warmer. But the ball is losing some energy through heat. And then it comes over here And it's lost half a joule as heat energy, and then it still has 4.5 joules of energy, and it smashes into the purple ball. And it transfers all of its kinetic energy to the purple ball. And so the purple ball goes rolling off, and now the kinetic energy of the white ball is 0. So the initial was 5, and the final is 0. 0 minus 5 is minus 5, right? So the change in energy is negative 5 joules. Work accounted for minus 0.45 joules because it did work on the purple ball. And heat is a loss of 0.5 joules because it lost energy to the table as it rolled. And the sum of Q and W is equal to delta E. So we can say that delta E system, the energy lost by the first ball, is equal to negative 1 times the energy for the surroundings.
Say they were just to keep bouncing back and forth. Eventually they would both lose energy because every time it transfers it loses something to E.
Right. So, young children love playing with pool tables. They don't play it the correct way. We've probably all done this. You stand at the end and you just roll the balls as hard as you can, and they bounce back and forth, and it's really cool and everything. If you roll one ball as hard as you can, it'll roll down here and hit the bumper and roll back, and depending on how powerful you are and how good the table is, you might be able to get it to go back and forth a couple times, but it's going to go slower and slower and slower. It's going to lose some energy when it hits the bumper, and it's going to lose energy as heat as it's experiencing friction with the table. And so in physics, when you're trying to study physics principles, I guess, yeah, they've created all these different ways to approximate zero friction. And so they have these, they're like air hockey, but it's a long track. And so it has air blowing up, and the thing that's sliding on the track is saved from friction because it's riding on air. And so you'll have a lot less friction, but you do still have some friction. And so you can get that thing going, and it's still going to slow down, but maybe just not noticeably in the parameters of the experiment you're trying to do. So let's look at what would happen if we've got an old, abused pool table where the surface is very rough. Now, if we think about rolling a tennis ball or maybe a chuck-it ball. I played fetch with my dog, 6:15 this morning. So we throw the ball, the dog gets it, but what if we roll the ball on the grass? Is it going to roll very far? No, because the grass is very rough, right? What if I roll the ball on the sidewalk? It's going to roll much further, right? Because the sidewalk is smooth. So the previous table is like the sidewalk, and this rough table is like rolling a ball on the grass. So as this ball that has the same amount of kinetic energy to begin with rolls across, it's going to lose more energy as heat to the table due to friction. So it's going to lose 3 joules instead of half a joule. When it comes over here, it's only got 2 joules of kinetic energy left that it transfers through work to the other ball. The change in energy is the same. The change in energy is a state function. Doesn't matter what kind of table you roll the ball on. The final was 0, the initial was 5, the change is -5. But W and Q are different. They still add up to delta E. But here, W, the work, was -2, and Q, the heat, was -3. But again, delta E for the systems is equal to negative delta E for the surroundings. And you can also say that delta E for the surroundings is equal to negative delta E for the system. Because I just multiply this by -1, and multiply this by -1, and then those negatives become a positive, and they're just opposite in sign. Any questions? So I pretty much already said that. So a cylinder and a piston assembly, and we're defining that as the system, is warmed by an external flame. So that flame is not part of the system. The contents of the cylinder expand, doing work on the surroundings by pushing the piston outward against an external pressure. If the system absorbs 559 joules of heat and does 488 joules of work during the expansion, what is the value of delta E? Well, let's pull the numbers out and write them down. That's a general problem-solving strategy. So 559 joules, 488 joules. And they're asking us, what's delta E? And delta E equals something. Well, this is 559 joules of heat. What's the symbol for heat? Q. What do they choose Q for? I don't know, but that's what it is, so we have to be okay with it. So Q is 559. There are no negative signs in this problem, and so we can't just assume that that means they're all positive. We're using words to describe the direction of energy flow, much like we use words to describe the direction of money transfer. If I say, I paid you $5, I don't say, I paid you -$5, but it is -5 in my bank account. But the word paid tells me that I'm losing the money, someone else is gaining the money. So if this absorbs energy, is that positive or negative for the system? It's positive. So I don't need a positive sign here, but just to emphasize the point, I'm going to put a positive. And then it says it does 488 joules of work, and the symbol for work is W. That makes a little more sense. So W. Here, the system is doing the work. Is that work negative or positive? It's negative. If the surroundings were doing the work, it would be positive for the system, because the surroundings are cleaning my kitchen or my bathroom. This is me doing something for the surroundings. So there, I've identified what those things are, and the change in energy is equal to the sum of Q plus W. So delta E is equal to 559 joules plus negative 488 joules. Do not overthink this. When you put this in your calculator, you can type it in just like that, and your calculator will understand what you mean. So 559 plus negative 488 equals 71. So the change in energy for the system is positive 71 joules. So there was heat that came in and work that went out, but overall the system gained energy. That means the surroundings lost energy. Any questions? $71 joules.